Well, good morning, good afternoon, good evening, kia ora, and good day. I hope you are all well, and welcome to the fifth of our series of webinars. Today we're going to be talking about the Del Mar Oceanographic wire walker and the use of the RBR loggers. But before we do that, as usual, as we're hosting this from Hobart in Tassie in Australia, and in the spirit of reconciliation, RBR acknowledges the traditional custodians of country throughout Australia and their connections to land, sea and community. I pay my respects to the elders past and present and extend that respect to Aboriginal and Torres Strait Islanders peoples today. Welcome everybody. The presentation will be split into 5 parts, and as we go to the next couple of presenters, I'll introduce them as we go, but I'd like to welcome Greg Johnson and Drew Lucas to today particularly, and thank them for taking part. We'll do questions at the end, but as always, we've got the very capable Eduardo and I believe Dan online as well, and they can answer your questions as we go through the chat function. So the session will be recorded. I have started that so that it can be replayed on our website and followed up later. And I'll ask if you can turn off your cameras and mute your mics as usual. The internet here in Tassie has been very slow over the last 24 hours, but hopefully we'll survive today. Before we fly into that, I just want to do a bit of an advert. Next week at 2 a.m. Thursday time, which is a sensible time in North America, Keu Stringari will be dialing in from France, and it will be presenting on how data collected from solo Ds can be combined with artificial intelligence to help provide crucial information in surf and swash zone dynamics, which will be very interesting. He's a University of Newcastle student here or ex-PhD student in Australia, but he's back in his native France. And then in this more socially friendly, certainly for us in Asia Pacific times slot, we're starting a new concept, which we're calling Ping the President. Trump wasn't available, so we'll be using Greg Johnson, RBR's president. And it's a great opportunity to put him on the spot to answer questions from me and hopefully from the audience about a specific topic or area. So the first one in this series, we're going to be focusing on RBR instrumentation and getting the most out of that. So I imagine that there'll be lots of questions about regular servicing, O-rings, cleaning of the sensors, how long you can put it in vinegar, how strength of vinegar, battery chemistry, all that sort of thing. And I'm sure we'll also talk about conductivity proximity. Yeah, conductivity proximity, because that gets asked a lot. It's a perfect opportunity to ask absolutely anything, and hopefully, nobody knows the instruments better than Greg. And it's a great opportunity for you to extend exactly what you're doing with your instrumentation. Okay, so the outline for today is I'll do a very quick overview. Then we'll introduce Greg to you, and he'll do a review of the sensor systems that go onto the wire walker, the RBR component of it. Drew will come in then and talk about the mechanical systems. Normally Chris Kontoes of DMO does this, so he's not available today, unfortunately. So Drew's kindly agreed to take that on. And then Greg will come back in, we'll talk about the data and telemetry, getting the information from below the water up to the outside world. And then Drew will do a presentation on some of the science and exactly what you can do with this very capable system. And it's a very, very interesting. I've seen some of Drew's presentations on the science side. It's really fascinating exactly how capable this is. So just very quickly, RBR has been making instruments. We're heading up to our 50th anniversary in a couple of years' time. And we start off with the very small sensors you see on the right-hand side. And then the compact loggers, which are self-contained instrumentations for temperature, depth, dissolved oxygen, PAR, very capable. We're on off a single AA battery and sample up to 30 million readings on a single AA battery, and that's any chemistry. Then we move to our standard loggers, the white loggers with the red end caps. and they are single channel virtuosos and dual channels, but also the CTDs, which I've shown there in the compact form factor and the standard concerto. So these can be mounted onto the wire walker, but normally people like to add a couple of other sensors to that. So the concerto with what we call the Sputnik connectors there can add another 2 channels. But of course, anything we produce, people want more data. So the Maestro there, the biggest instrument on the screen, can take up to 7 additional channels. So that's normally CTD plus up to 7 other channels. We've got external comms for the standard loggers, and so as well as the 240 million readings you can store internally, and they run on more battery powers, 8 AA batteries, again, any chemistry. And then holding all this together is our in-house software, Ruskin, and Ruskin has been designed as one app to rule them all, and that'll get repeated by Greg, I'm sure. And the idea of that is that no matter what instrument you use and what sensors on that RBR instrument, you run it all from the single piece of software. So that's just a fraction of the instrumentation. And again, this screen shows you a whole assortment in our weaponry. And I won't go through them all. You'll be very pleased to know that. We're today going to be focusing on just a few of them. Drew will be mentioning on the bottom left there the wire walker mechanical components of this presentation, and then Greg will work you through the loggers on the right, inductive modem in the middle, the battery packs, the Fermata, and the Cervelo comms unit. So with that, I'll hand you over to Greg. Are you online, Greg?
I think I'm online.
Perfect. I can hear you clearly, and the fact that you answered means that everybody's been able to hear me, which is a great relief. Greg, just in 30 seconds, do you want to give a quick summary of your background and how long you've been with RBR?
Sure. I guess I started off life as an electrical engineer. My working life as an electrical engineer, electronics, and then I got distracted by material science and X-ray imaging. But I've always been involved in instrumentation of one kind or another. And I've been at RBR for, working for RBR for about 12 years, and actually based in Canada for just around 10.
Excellent. Okay. And we always put this on all the other presenters, so it's only fair I put you on the spot and ask you to give us a fun fact that maybe even I don't, and I've known you the whole time you've been at RBR, but maybe a fun fact that none of us know about you.
See, of course, I prepared my classic one. But I think you probably know it, and that is that I really like to fly boats. So boats that don't touch the water very much are, well, you know, I'm in my late 40s, I'm about due for a midlife crisis, and having something that goes fast feels like that. So foiling catamarans are, in fact, you catch me now under this very dim lighting in an Airbnb in Quebec City, where I've been for the week, and traveling in, let's see, what units would you like? I think 23 knots, 40 kilometers an hour, 30 miles an hour, something like that is wow. Yeah, what have we been doing this week?
Excellent. Well, while we've got internet connection, let's move on, and thanks for sharing that, Greg. Over to you.
It's always difficult when talking about the wire walker system to decide where to start. And in some ways, I often think Drew is the great place to start with the science and the application, which motivates so much of the development that's been done both at DMO, at Scripps, and here at RBR around achieving some phenomenal results. So this is a somewhat arbitrary place to start. It's with really the sensing end of the electronics chain that is going to be on the wire walker itself. And you'll find out, if you don't know what the wire walker is, then well, you'll find that out when you replay the video and you reverse it all in your head, and you'll understand. So so many oceanographic instruments really start off with CTD as the main tool in the toolbox, and the Wirewalker is no different. So we're using here the Concerto CTD, which is a very low power inductive measurement of conductivity. And that provides WOS standard accuracy of about 3 microsiemens per centimeter, temperature 2 millidegrees, and temperature and pressure that's proportional to the full scale pressure, but typically about 0.05% full scale. The instrument has no pump, and it has a very short, low aspect ratio conductivity cell, which means that no pump is actually required to get great flushing. You can see in the render that's on the screen that the temperature sting, which is the very thin hypodermic needle-like part on the upper part of the conductivity cell here, it's actually co-located in the direction of travel of the instrument, which is the way it's on the screen is from left to right, but normally on the Wirewalker it's going to be left would be further down, and it will be moving upwards through the water. That's co-located with the conductivity cell itself, which is you can see the inner bore of it, the white circle there. And the reason that's important is because it minimizes salinity spiking before you do any post-processing at all. And it makes treatment for high gradients much, much simpler. The Concerto is able to record about 240 million readings internally. That's less important in this application, of course, because we're going to be telemetering the data in real time up the line and to the surface through satellite and back to the office. But in an autonomous mode, the instrument has a tremendous amount of internal storage. The CTD itself can run up to 32 hertz. There's a variety of pressure housings that are available, and then multiple pressure ranges within those bands. All our instruments have USB-C, and it shouldn't be a surprise to you. Every instrument that's worth its salt is using USB-C these days. But one of the things that is slightly unusual is to have twist activation. So you don't need a computer to start or stop the instrument. You simply grab that red end cap at the far end of the rendering there and rotate it a few degrees, and the instrument will buzz in your hand. That means that even on a ship with the engine running in broad daylight, you can tell that the instrument's running, the batteries are correctly installed, and be confident before you deploy. Wi-Fi means that you can get the data out even if it's still hanging on a winch, for instance. Now, some of those things only apply to the autonomous use of the instrument, but the direction-dependent sampling is something that we developed expressly in conjunction with the folks at DMO and Scripps. And what that permits is the instrument to autonomously determine which way it is traveling in the water column. Is it coming up or going down? And then you could say, well, on the upcast, as is customary for the Wirewalker, where we're taking the finest resolution of data, I'd like you to measure at full speed, maybe 8 or 16 hertz, depending on how many channels you have. But on the way down, we don't want you to consume as much power. The data isn't as good quality because the water is flowing over the Wirewalker body before it gets to the sensors. So we really just want enough to get some housekeeping to ensure that there are no mechanical snags, that the system's still operating. And that reduces power consumption dramatically when the instrument can itself determine when to change the sampling rate. As Steph highlighted for the other instruments, we use AA batteries everywhere, and you can use the best lithium thionyl chlorides for the best and longest deployments, but you can also go all the way down to alkalines that you get from the corner store, or even rechargeable nickel metal hydride batteries. Their capacity is much lower, but of course, if you're only using the instrument during the day and you can recharge the batteries at night, that's absolutely adequate. Have the next slide, please, Steph. It looks like Steph's laser pointer is stuck on him. Try the right arrow key or down arrow key if nothing's working. Oh, it looks like Steph's really stuck. Oh, there we go. Splendid. So we can take the CTD and augment it, as Steph mentioned, with a couple of other channels. And we usually do that using the arrangement that will make sense to those of you who either were around when it happened or have been reading about space history enough to know what Sputnik refers to. And that's these two additional connectors that are slightly reverse angled. We can cable on two additional sensors there. And in the render at the bottom, you can see an example with oxygen and turbidity. But those can be any of the sensors that we support. That allows you to have a 5-channel instrument in almost the same form factor, regardless of whether you clamp the sensors onto the instrument itself or onto a cage, or in the case of the wire walker, mount them somewhere completely different, facing in a different direction for reasons that will be explained later. Next, please. The Maestro is our bigger instrument. As Steph said, it's up to 10 channels rather than limited at 5. And really, we call it the Maestro because it's the instrument with the big head. And that's so that we can physically accommodate those additional sensors and nothing more than that. The rest of the instrument remains identical. Next, please. Now, for medium-term deployments, and because we have very low power consumption, the instruments run off internal batteries with more than adequate deployment times. But in the case of the wire walker, we really want to be effectively operating like we were on a profiling winch, but not just out on the side of the ship for 5 or 10 hours, but out there for days, weeks, and months. And so in the case of the wire walker, we provide also an external battery pack. Those of you who learned to play piano as children will perhaps remember with horror the symbol that's displayed above the fermata. It's the one that in the musical notation indicates that you should press and hold the last chord of the piece. And its literal name, fermata, means to prolong beyond the normal duration. And so we use that for this battery pack. It has 56 D cells. If you use alkaline, that's about 1 kilowatt hour. If you use lithium, that's about 3 kilowatt hours. But we would rather not sell you batteries. We think that batteries are not something that should be proprietary. And so we supply the drawings for you to make your own packs anywhere in the world. It also makes it much easier for transportation if you can source the lithium cells locally and pack them up yourself. Next, please.
This is
I'm going to go over to Drew.
Are you? Let me see if Drew's unmuted. Are you there? Morning, Drew. Good evening, your time.
Yes, it is. It's not quite as late as Greg, but I am here, and I hope you can hear me.
Yep, I hear you loud and clear. Welcome, Drew, and thank you for taking part in this today. So it's great to have you on board. So, Drew, you wear several hats. You're partly obviously involved with Del Mar Oceanographic, but also you have joint appointments with Scripps and the Department of Mechanical and Aerospace Engineering at University of California, I believe.
That's right. Yeah, thanks, Steph and Greg, and I'm glad to see a lot of folks here and some familiar names, at least. Yeah, my name is Drew. I'm a faculty member at Scripps Institution of Oceanography and in the Department of Mechanical and Aerospace Engineering. I'm an oceanographer, and I am a co-founder of Del Mar Oceanographic, which is a company that's based really on one product, and that's the wire walker. So I'm going to tell you a little bit about the wire walker and how it works right now. And then I'm going to tell you a little bit about what I fell in love with about the system, and some of the science that's a little bit that I'm doing right now. And so if you can go to the next slide, please, Steph. Before I get into the wire walker, I do want to give a tiny bit more history of the point out some of the things that have really been wonderful collaborating with RBR, both at Scripps Oceanography and as Del Mar Oceanographic. When I started working with the wire walker over 15 years ago as a baby graduate student at Scripps, the instruments that were available, which are great instruments, Seabird CTDs, were not optimized. I found out quickly, not optimized for what I needed, which was high resolution measurements, rapidly collected because the vehicle travels, and low power. And I struggled through that. I did my PhD with Seabird instruments, and then I learned about RBR, and Greg in particular, and RBR as a company, really understood the, what I needed as a customer at that era, and made just incredible efforts and investments into, saw the value of the platform, and really worked with us to optimize their sensors for our platform. And that is something that I didn't gain a lot of traction with other instrument vendors. Although, anyway, so that's one, is that, there's been, and you'll see a bunch of that, and really thank RBR for that. And the other is that, and I think I've said this to Greg before, is that it was very refreshing to use Ruskin. This was many, many years ago now when I started using it. But to use a instrument in interrogation software that ran natively on my Mac, that was modernized for fast data upload and download, all that stuff made a huge difference to me. Now it's a little bit more commonplace, but then it was a big deal, and I really fell in love with the sensors. So, and here we are 10 years later, and the Delmar Oceanographic is happy to support any instruments that work with our platform, and really RBR are the ones that are the best for that. Okay, so you're looking at a picture of a vehicle, of a wire walker with its cowlings on, lying flat on the deck of not the deck, the forward area of a small whaler. The wire walker is, you can go to the next slide, please. I think it gives us a little bit of, ooh, look at that. Something just appeared. One more, please. The wire walker is a combined system. We'll go back to the profiling vehicle. What you were just looking at is the bit that goes up and down underwater. It's really a combined system that is composed of a surface buoy, a wire under tension with a weight underneath it, and then the vehicle you just saw. The vehicle itself is not very big and not necessarily very heavy. You saw it in the front of a small boat, and we do very commonly deploy from 3-meter and size vessels all the way up to global class oceanographic vessels. The surface buoy is also meant to be handled or handleable. You can see it's just under 1 meter in diameter. Here you're looking at it sort of facing tilted towards you. Inside is the RBR developed telemetry system with a iridium antenna sticking out of the top there. And the buoy is sort of there just to follow the ocean surface waves. We mount up beacons, flashers, et cetera, that come with the basic package. Next slide, please. We call it the wire walker because it runs on a wire. And a wire is, when I say a wire, I mean a cable, a jacketed steel cable. The cable that we use is 3/16 inch diameter. The wire part is with the jacket on it, it's about 1/4 inch. These wires we get primarily from a company in the United States called Mooring Systems. The terminations are swaged, and they can be either like you see in the big picture, which is just to connect to the surface buoy and the bottom weight, the terminations, or they can be actually equipped as a hammerhead. A hammerhead is used to enable inductive communications. So that's a setup that we've built at DMO to handle the inductive connection between the profiling wire and the surface buoy. The beauty of this is that we can communicate, thanks to Greg's inductive communication system, RBR's inductive communication system, we can communicate on the same wire that we profile on. And so we're in constant contact, surface buoy with the profiler, which is very nice. And this wire can be arbitrarily long. We typically do deployments up to 500 meters depth, but we can go deeper if necessary. On the other hand, we deploy this stuff in the coastal ocean with very short wire lengths. I've put them out with 5-meter wires on them in 6 or 7 meters of water. Next slide. And so that's an important point because of the fact that the system has to operate under tension. You can see there on the left, there's a kind of sketch. There's a surface buoy, a black line going downwards, and then what we call the downweight. Downweight is just simply galvanized steel plate. They're about 20 kg each. We will typically put on 2, depending on what we're doing. And the beauty of this system is that as long as that surface buoy wire and weight is all under tension, that is, it's suspended from the surface, it can either be deployed in a free drifting mode, or the suspended weights can be attached via a mooring line to the ocean bottom. So these work as moorings or as drifting vehicles. Like Greg was saying, this is sort of a reverse webinar, and I am doing sort of a reverse presentation of the wire walker because I haven't yet told you how it works. And that's what's coming next. You can see that bouncing up and down. Next slide, please. Okay, so the profiler itself is 1.5 meters plus tall, 24 inches, so 62 inches tall, 24 inches in width, and 6.5 inches in thickness. It's got an aspect ratio that is on purpose, and that is to allow it to vane into the oncoming current. If you can look at the rendering, the small rendering on the left, you can see an RBR concerto mounted up on the leading edge of the wire walker, and that is to allow the greatest amount of undisturbed flow through the conductivity sensor. This vehicle profiles continuously in the vertical direction, powered only by environmental energy, by surface waves. I'll explain in a second exactly how that works. But what that does is it takes Greg's instrument, which is sampling very quickly in time, and it adds a spatial dimension to that instrument. So all of a sudden now we are sampling in time and depth. And adding an extra dimension to your data is exactly what the wire walker does. And I'll show the scientific reason for doing that. Okay, next slide. Okay, so this is a Proteus mooring simulation animation. Let's click on it, see if anything happens. I don't actually know, I can't quite remember what the simulation is exactly got in it, but it is showing the surface wave field, and I think it's a couple meter waves at 8 to 10 seconds, and it's probably pretty high bandwidth. So let's just I'll show something that's a little bit lower bandwidth. Can you click through the next slide for me, Steph? We can talk, you know, if folks want to talk about Proteus and the wire walkers, I'm happy to answer questions about that. Proteus is a great mooring software, and we've been working with Proteus to make these simulations even more higher fidelity. Next slide, please. Okay, so this is a little bit more my speed. This is a stop motion animation of how the vehicle works. So if you click on this, let's see if we can see this come through. This was made by colleague Melissa Omand, who's a longtime user of the wire walker. So it's 500-meter wire in this case. She did this for public outreach. The vehicle goes on the wire. The wire runs right through the middle of the vehicle. And inside of the vehicle is a mechanism that turns the two-way motion of the surface buoy, riding the surface waves, into one-way motion of the vehicle. So there's the vehicle descending downwards, that camming mechanism. It's grabbing the wire on every downcast. No electronics, no switches, no batteries, nothing, just purely mechanical. The bottom of its profiling range, the cam is released. We ballast the vehicles to be positively buoyant to achieve a ascent rate of something like 50 centimeters a second. They come to the surface. We're collecting high resolution data the whole time. And then at the surface, the cam is mechanically re-engaged and it heads back to the ocean depths. And it's really just that simple, except for the fact that, as all of you know, being ocean observationalists and technologists, getting something to work in the ocean is difficult. And the choices that Del Mar Oceanographic has made has always focused on simplicity, because we believe that nothing is more important than the thing working. And we, you know, we learned our lessons the hard way. This came out of 20 years of development at Scripps Institution of Oceanography and deployments all around the world. And although it seems simple, we've spent an enormous amount of time and effort optimizing every detail of the mechanical parts of this system for ease of use and reliability in the field and robustness in serious wave conditions, which we've faced. Next slide, please. Okay, this is a rendering. Okay, yeah, why don't we just click through? We'll see what this is together. Aha, yeah, so there's the cam. We provide foam, so we will ballast your vehicles with whatever instrument integration that we put on there for you. We build customized instrument clamps. We fabricate those. We have years of experience building and fabricating this type of these type of fitments for instruments. And then we encase the whole thing in cowls to keep it safe. Next slide, please. All right, here's a pretty picture with some really nice RBR gear. Again, I think this is the last slide in this part. I really do want to emphasize that it's been a pleasure working with RBR. What you see here is a fitment of a concerto and a fermata. This would be good without auxiliary sensors for months and months and months. And would never stop profiling. I should mention the profiling speed. The rule of thumb for us is that our vehicle will do a round trip 100-meter profile, so the surface down to 100 meters and back to the surface every 10 minutes or so. And it scales like that. So 500 meters is about 50 minutes. Typically do a little bit better than that. And that's continuously. So you're talking about, you know, minute by minute resolution of changing physical and biological and chemical dynamics of the ocean from the same CTD that you might put on a vessel and do a few casts over the course of a day. All right, I think that's probably done for me, and then back to Greg. Oh, look at that, there's more pictures. Those are also nice pictures. Lots of different instruments. I'll show you data from these instruments. Click through one more time for me, Steph. That's a beautiful integration from the University of Hawaii at Manoa, measuring biological variability in concert with physical oceanography. Next slide, please.
Can I just add to this, Drew?
Yeah.
Obviously, that you guys have got the expertise and to put all this together, and so you obviously work really hard to make sure that the sensors are pointing in the right direction. So they, you know, the optical sensors are pointing out to the side, so they're not affected by the light, except the PAR obviously looking at the surface. So just wanted to add that. Yeah,
thank you, Steph. That's a really important point. You know, we've integrated a whole bunch of different things. You can go forward one slide to that one you had up there. It's a good, nice example of what I was just about to say. So these are some integrations we've done over the years at Scripps and DMO. On the left is a underwater microscope, 2 focal length microscope that can collect images and then does machine learning to categorize those images. In the middle is an integration with a Rockland Scientific microstructure sensor. We've had good experience with that instrument, and Nicole Jones at the University of Western Australia has a package that includes that, but RBR CTDs and other instruments. And finally, we also have been integrating and having very good luck with the Nortec, which is the bottom right of the rightmost picture, the Nortec signature series of ADCPs. We typically point those downwards and get extremely high resolution of ocean shear, ocean currents, as I'll show in a second. Next slide. Can't believe how many slides Chris has. Okay, I will talk about almost every one of these applications, so I will kick it back to Greg.
The good stuff, you have to wait for another few minutes to see it, but it really is fantastic to see some of the data and the analysis that gets done once you do this. But we're going to take a short diversion by way of talking about how does the data actually get back to the user. First of all, it's important to say that although the logger underwater is storing the information internally, it can only store, and I say only in parentheses, in guillemets, entre les guillemets, what are they called in English? I've been in Quebec for too long. Quotation marks. It can only store 240 million readings at a time. And so the first thing that we do is we use our inductive modem to bring that data up to the cervello, the brain of the system that's sitting at the surface. And the inductive modem has a small electronic component, but it also has this ferrite clamp that is mounted inside the wire walker, and the wire passes through it without being clamped at all. And just passes through without any friction. So you can see there's no tools required here. This is just a hand-operated clamp that's nonetheless very robust to being shaken and vibrated and strummed on the mooring line. It provides an inductive modem that will run at 4800 baud that in other applications you can use as a standalone modem. It's completely transparent. Just like a telephone, it doesn't really care whether you're speaking English, French, or Chinese. It just knows how to pass data. And that's the same with our modem. It doesn't matter if you're connecting it to an RBR instrument or a Nortec Aquadop or to a Teledyne ADCP. We have our friends, but we like to support everybody. This is fast enough at 4800 baud to allow us to get 5 channels of data up the line at 8 Hertz in real time. And if the cable is damaged by accident on the deck or any other reason, the instrument and the inductive modem will still work above that damage point on the line and continue to telemeter the data, even that data that was recorded below the damage point. As Drew was mentioning earlier, there are 2 different designs for the jacketed cable, one which is swaged at both ends and one which has this so-called hammerhead that is really just a strain relief for the electrical system, and this is tolerant of both of those. We'll look at the next slide, please. You can't quite see in this picture, but the electronics are indeed attached to the rear of the concerto and make it a little bit longer. And the ferrite holder is, believe it or not, inside that ellipse that's in the center. But it is clamped around that mooring line that's passing through the center of the instrument, through the center of the wire walker. Next slide, please. It's amazing to think of all the bytes traveling from Hobart to Quebec City and then out back to the world. In that particular picture, there was also, don't move the picture again, but there was also a shot of the Nortec that Drew was mentioning and the location of the Fermata extra battery pack. This is more a kind of exploded diagram, if you will, of how the hammerhead is put together and taken apart. And the very neat appearance that you get at the end. Neat not because it's cool, but because simple is indeed better. And having something that has as few parts as possible, especially moving parts, always a point of failure. But to be able to do, to be able to handle that simply is important. Next slide, please. This is another view of the buoy, the buoy that DMO provides at the topside. And the cervello is dropped inside and was custom built to fit into the wire walker buoy. So we call it the cervello because it is the brains of the system. It is your first point of backup for the data that is on the instrument below. So if the worst was to happen, and for whatever reason, the chain, the mooring line was to part, the data is safe at the surface already. It has really only one interface that a user can see, and it's a USB stick. and you attach your USB stick, your memory stick to it. When you open it up, the light turns red, which indicates don't take it out. And when the light turns green, all your data has been automatically downloaded onto it. You can also reconfigure the sampling regimes and the deployment schedule by putting a file onto that USB stick and inserting it, and the instrument will ingest that. Now, as Drew pointed out, this antenna that you can see on top is the Iridium antenna. However, the device always comes with also a GSM cell phone modem antenna, which is less sensitive to obstruction, and so it's actually mounted underneath that top plate. And preferentially, the Cervelo will choose to use the GSM network when it's within about 20 kilometers range of a base station. Usually that's also equivalent to 20 kilometers from the shore. However, as soon as the wire walker by design drifts out of range, it will switch over to the slightly more expensive but tremendously flexible Iridium system. There's also a second debug port on the top there. You can just see next to the head of that is Susan Wiffles from Cesaro in Hobart, signing off on the deployment from the investigator last year. There is a debug port that can be used for a variety of purposes. Next, please. We have a web-based simulator that allows you to calculate how long the batteries are going to last. And so in the middle of the documentation, you can run this deployment calculator when you're browsing this documentation online. And it will allow you to say how often you plan on getting a GPS measurement, how often you would like to have telemetry, what kind of modem you expect to be using, and what sampling rates you like to have. And it will therefore tell you what, using either the alkaline or lithium version of the RBRfermata, what is the expected deployment life. Next, please. So the data is available through a web portal, which can be password protected to keep your data safe. That accepts the data coming in from either GSM or Iridium. We host the data with two locations possible. One is in North America and the other is in China. Very simple charts of time series, and also these fascinating depth plots that Drew's going to show a lot more of. But there's also, without needing to use a web browser, there's a very simple API that allows you to pull data from any terminal program. Here is an example in the top left of the language used for curl, where we're simply saying, yeah, please go off and get this compressed data. And we'd like you to retrieve from 2016, September the 8th, to 2016, September the 9th. That is to say, 24 hours worth of data. We also will give you an example of how to use rsync, which is a tremendously helpful low bandwidth solution for pulling down the data and incrementally adding to it while you're on the cruise. So you might have deployed the wire walker and then you set off, maybe you're going to steam butterflies around it, bow ties around it rather, and do some other deployments of other instrumentation. And you want to get the live data onto the ship as quickly as possible, but you don't want to burn the ship's satellite network connection by re-downloading data. And these scripts make that very easy for you. Next slide, please.
That's just about finished with you, Greg, I think, till the questions, and we're heading to Drew's. We'll head over. So I'll stop sharing my screen if I can. Let me turn that off. Excellent. Drew's taking it.
Can you see my screen?
I can, and it's, yep, it's opened up to the It's actually on
Is
the,
it presenter mode?
yes, exactly.
Sorry, I will reshare. Let me try that one more time. Okay, you see probably a MATLAB window.
Now we're seeing a variety of MATLAB and terminal.
There you go.
Yeah, sorry. Okay, there we go. I do a fair amount of Zoom teachings, so sometimes I can get that right.
Just before you go on,
Okay.
Drew, if you want to move your chat window, that's blocking some of the screen.
All right.
The rest of it.
I think we're there now.
That's it. Perfect. Leave it to you.
Okay, so I've already introduced myself, and we are moving along, but I just want to motivate a little bit about the scientific exploration, and this is probably too low of a bar, but I will go through it anyways quickly. So why did I fall in love with this platform? And it's kind of summarized by this. So you have a traditional mooring, which Greg really likes because you buy lots of CTDs, and you put them at some distance away from each other in depth, and that whole thing is vertical up and down the ocean. That's pretty great. That measures a very specific thing. So here's a little schematic of the ocean, and there's warm water at the top and cold at the bottom. And I've drawn a little bit of a wavy pattern in there. And what that represents in this case is the presence of internal waves or motions of the thermocline up and down. Whoops, wrong direction. And so those waves, that variability in depth is constantly in motion. So that is to say that these depth, that the vertical distribution, in this case of temperature, is constantly changing. And so if you're looking at a particular instrument at a particular depth, the way that you see that is as a time series, where in this case, the water has started cold and then it's gotten warm. And that's pretty good because as long as you sort of understand the vertical distribution of temperature well enough from all of your measurement locations, you can turn these discrete measurements in depth into some type of map of the entire ocean. But the real ocean is a little bit more tricky than that, and here's kind of an example why. So here's one example, which is pretty common, and you guys will have all seen this before. And this is a depiction of the ocean or a lake when it's very stratified. And so what that means is there's a layer that's warm but it's very homogeneous, then there's a layer of very strong gradient in temperature, and then there's a layer below that is cold and pretty homogeneous. And so if you imagine sampling that, that's a little bit more tricky with your distributed sensors, because really only one sensor is exposed in this rendering, is exposed to variability. But still, maybe you can make some assumptions and get back to the full water column from this. But what we find when we look in detail in the ocean, that it's rarely even that well behaved. Here's a good example of what it looks like off of Scripps Beach. The thermocline goes up and down, but for some funny reason associated with the submarine canyon just offshore of us, the top of the thermocline goes up when the bottom of the thermocline goes down. And that creates a very weird pattern in temperature that you'd have a hard time figuring out if you had very dispersed sensors. Now, this gets even worse if you start adding sensors that are of other channels that are expensive. So here's a picture of maybe adding some fluorometers. You really need the same number of fluorometers as you do CTDs to get a really detailed picture. And of course, maybe you care about dissolved oxygen or turbidity or many other channels, radiation. All of those things would require, of course, separate sensors in separate locations. And so in the NODA sort of side of things, if you can move a sensor package up and down, that really helps. And the way that we talk about that scientifically is we talk about what are known as isopycnal coordinates. And so this is a way of thinking about the ocean that's a little bit different than normal, or that you might be used to. And that is thinking about the ocean not in terms of its variability in depth, but instead mapping the variability of the thermocline or the isopycnals or the chlorophyll maximum or the dissolved oxygen minimum in the vertical in time. And by that mapping, it allows us to track the depth of the isopycnals, and thus we can remove the effect of the isopycnals heaving up and down and look at the variability of the ocean in the frame of reference that is tied to the surfaces of the internal surfaces of the ocean as they are wafted around. We call this an isopycnal frame of reference. And so this is extremely, extremely valuable scientifically because it deconflicts or demystifies the ocean that variability at a particular location and depth is always contaminated by the vertical motion, not contaminated, but influenced by the vertical motion of the ocean, whereas a full depth, high vertical resolution profile is not. And that allows us to study in more detail how the ocean changes in time and in space in a way that really was invisible before the development of autonomous platforms. So this is a recent deployment that we did. This is off the back. This is the Sally ride. That's a Scripps vessel. It was in the northern Indian Ocean. And this was a really great collaboration that I've been doing with Woods Hole Oceanographic. Tom Farrar and Bob Weller at Woods Hole build these big surface buoys. Well, these are their medium-sized surface buoys, I should say. But on this surface buoys, a full air-sea flux package. And then below the surface buoy is a wire walker vehicle. And that whole thing is tied together with inductive communication and real-time data telemetry. So we deployed this in the middle of the northern Indian Ocean, the Bay of Bengal. We're working there to understand the monsoonal variability in air-sea interactions and how it influences weather forecasting. This is money provided by or effort supported by the Office of Naval Research. So we typically do this often with these vehicles. We'll put them in the water. We will then follow them with the ship. So we put out 3 wire walkers with these air-sea flux buoys on the top. We followed them with the ship for 2.5 weeks. The black line is the ship track. We did all sorts of other sampling in their context. This allows us to ground our ship measurements in this frame of reference. It's both moving with the mesoscale. The color on the right are the mesoscale ocean velocities, and is decontaminated in the fine scale. That is to say, we're able to track the internal waves moving through the array, and thus measure variability on these material surfaces. So this is what some of those data look like quickly. You're looking at 250 kilometer long drift. This is 12 days, I think. 100 meter wire, in this case, almost 2,300 vertical profiles. This is salinity. The Bay of Bengal has a lot of fresh water in it. And you can see the incredible detail of salinity that we can see here right in the middle of this plot. I am not able to, let's see here. Let's see if this works. Kind of. This is the influence of some fresh water that's come off the coast and actually a little bit of rain. And we're able to also see these black lines are the isopycnals that I mentioned. They're getting heaved up and down by the internal waves, the internal tide. And then on top of that is this very fresh layer. And plotted on top of that is the net heat flux into and out of the ocean measured by the air-sea buoy. So we're able to capture the fluxes through the surface and the detailed vertically well-resolved response of the ocean to those fluxes. Okay, so a little bit more detail. This is the same exact plot. Now it's in depth versus time rather than depth versus latitude and longitude. Now it's temperature as well. You can see how well these beautiful maps of temperature. This is a single thermistor on an RBR concerto, just being moved up and down in the ocean for free by the ocean waves. The details of what we learned here is not that critical, although I will say that we are using these observations and turbulence observations on this platform to test the assumptions that go into weather forecast models and climate forecast models in order to understand how these small scale vertical processes change the answer when you know them, as opposed to climate models, which really do not know this level of detail. We codify that in what are called parameterizations for these numerical models. This is how we study that. Okay, so I'm going to show something that Greg has not seen yet. And this is a collaboration that RBR and a postdoc of mine, Tamara Schlosser, have begun to do. And we've just been messing around it a little bit in the lab, but we've managed to fit up a Satlantic, or now Seabird, SUNA nitrate sensor. That is the this pressure case here, to the Wirewalker vehicle. This was deployed for the first time in May, so these are brand hot off the presses data. This is integrated with a RBR system. It's actually the same system, the data that I just showed you. It's measuring CTD. It's measuring 3 bands of optical quantities: chlorophyll, backscatter, and CDOM. It's also measuring subsurface irradiance via this OCR 504, which measures in 4 different bands. So that's how much light is at depth. And then we've got this nitrate sensor on board. Greg is working with Tamara Schlosser as part of RBR's really nice postdoc program to integrate these 2 instruments together, the Concerto and the SUNA. In this particular proof of concept, we just acquired the SUNA data ourselves. The cool thing about this is right in the middle of an absolutely enormous red tide that we had this summer off of Scripps, and it was right in the middle of the beginning of COVID as well. This is Tyler Hewen here. He and I deployed this in the middle of the lockdown, and Tyler is one of the co-founders of DMO. You can see the picture on the bottom right is off of Scripps Pier, and this little thing is actually an osprey sitting on the shadow of an osprey sitting on one of the instrument arms that sticks off of Scripps Pier. See just how very dense that red tide was. So we had about 3 weeks of data, and the thing about nitrate is that we really want to know it if we want to know how the phytoplankton are responding or changing in time. Nitrate, at least where we are, is one of the rate-limiting nutrients. And forever, including in my PhD, we wrongly assumed that the nitrate density relationship was steady enough that we could basically assume that we knew what the nitrate concentration was from an autonomous vehicle by knowing the historical nitrate density relationship. And so I set out to test that. I kind of knew it was wrong, but I set out to test it anyways. This is 3 weeks. This is 100 meter. This is a moored instrument, 100 meters of depth, temperature, salinity. This is depth time plots, temperature, salinity, and nitrate determined directly from the SUNA V and SUNA V2. And the thing that you can see immediately on this is the pattern that you might recognize. Very low nitrate at the surface. Below the nitrocline, the neutrocline, there's high nitrate. But if you look closely, you can see all sorts of funny things going on. Places where the nitrate doesn't increase with depth. Here it increases with depth, decreases again, and then increases with depth. And this was very intriguing, and I believe the first of its the measurements that are the first of their kind, at least with this type of temporal resolution. And so we can, when we look closely, we can see that the variability, there's a variability in the position of the gradient. There is times where the gradient is not monotonic. That means it's not just increasing with depth. And if we compare that to the optical channels, we start to learn a little bit more. Here is chlorophyll fluorescence and backscatter. Both of these are measuring, in this case, this very dense and red tide. You can see these beautiful features of the chlorophyll descending with a regular pattern. So it starts up near the surface and it sort of descends, then it's back near the surface and it descends. This is actually, I'm not going to prove it here, but this is actually swimming of these dinoflagellates, Linglodinium polyhedrum, which made up this red tide. They swim down to a particular depth. You can see that all of the chlorophyll is above a particular depth, and not surprisingly, that is the depth of the nitrocline. So we're measuring directly, these organisms are swimming down and getting nutrients from depth at night along proposed but very difficult to measure thing. And so this is a very dense red tide. And I'm just going to show just a few more before, so I don't go too long. But let's look in a little bit more detail at what happens when the chlorophyll, which is representing the organisms, are really at high concentrations at the very top of the nitrocline. You can see this pattern where there's very little nitrate at the above the nitrocline. There was a very strong gradient, and that gradient has been eroded. And this is kind of a figure that you know, it takes a little bit of warming up to, but is really powerful. If we just look at the bottom panel, because I have this constant measurement of nitrate, and because I can map it to isopycnal surfaces, I took bottle samples to prove that the nitrate sensor was well calibrated, but I'm able to remove drift based on the fact that I'm measuring it across the entire range at isopycnal surfaces, all isopycnal surfaces, over all times that it's deployed. And so from that, I can make a nitrate isopycnal relationship that I can use to make an anomaly. And so what you're looking at here in the color now is not the nitrate concentration, but the anomaly of the nitrate with depth in this case. And you can see that that actually changes in time. These are big changes, up to 10 micromolar at the position of the nitrocline. So at the nitrocline, it is getting there's less nitrate, then there becomes more nitrate over a period of time, then there's less nitrate, more nitrate. These are cycles of many days. We don't know what causes them. But you can still see that there are these wiggles up and down. Those are the internal waves. And so what if I take the internal waves out in this way that I've discussed? So that's what this is. Now we're looking at the world through an isopycnal frame of reference. I've removed all of the internal wave heaving. We can see that this really demystifies what's going on. The swimming of the organisms is much more obvious. This is all swimming associated with organism motility. Increase in the organism concentration is here. Now, if you look at the nitrate anomaly with these waves removed, you can see this just beautiful signature of the variability of the top of the nitrocline, increasing and decreasing in both its thickness and its sharpness on the time scale of changes in the biology. And you can see this really amazing correspondence with the increase in fluorescence at depth with the drawdown of nitrate. And to prove to you that this is not physically mediated variability, I'm showing another quantity here, which is conserved. It's called SPICE. It's a relationship of temperature and salinity, not modified by organisms. And you can see how very different that is. So the summary of this was for a different, these slides for a different project, obviously, but the summary of this is that here is the time mean of the nitrate concentration against depth and its standard deviation, which I've just taken all the profiles and I've said, okay, what is the variability at this depth? But this is all on isopycnal and has been just transferred back into depth. And what we find is that on the isopycnals that are right in the middle of the nutricline, you're seeing plus or minus the mean. So the mean here is 5. The one standard deviation is plus or minus 5. And this isn't the instrument's bad or we don't know what's going on. This is the effect of the biology. This is precisely what we're trying to measure. And we can see how these things are related by taking this one nitrate sensor, putting it on this vehicle, moving it vertically in the ocean. This again would directly feed into a predictive HAB, harmful algal bloom forecasting model, because it would allow us to understand how do these rate limiting nutrients play a role in here. So we work in coastal water quality, many other things, but I'm going to just stop there. We're over time, and I will say thank you very much for your attention. You know, nitrate is just one of the things that's coming down the pipe for new channels. We're always pushing the envelope with scripts and a DMO, and we again appreciate RBR for making a lot of these dreams reality. I hope I've showed some data, and I'm happy to stay as long as folks want. answering questions about DMO, about the wire walker, or about these data.
That's excellent, Drew. That's really interesting. And there's new slides there, which I didn't see in the previous one. So that's fantastic as well. The way my brain works, I think the wire walker is a perfect tool because it shows it in such a graphical way that it makes it really simple for me as a non-oceanographer to understand. So that's great. So we'll open up the floor to some people to questions if anybody has one. While people are unmuting themselves and starting videos, etc. I do ask. I mean, obviously you've got to take into account tide and waves and everything to make sure that you keep the mooring taut. How close to the sea floor can you realistically get with the profiling? Hang on,
there we go.
Yeah.
Well, it depends on your tolerance for risk. You know, we you know, typically say that, you know, you take a average tidal range, you know, you look at your max, you know, flood tide height, you add a little bit, 15% to that, and then you figure out what your surface wave field might look like. And, you know, so if you have a 2 meter plus or minus tide, and you have, you know, 2 meters or 3 meters of waves, then you want to be, you know, 5 meters or above the bottom. You know, if you can constrain those variables I mean, the tide is perfectly constrainable, but if you can constrain the surface waves, you can get closer and closer. And we regularly deploy, you know, within a couple meters of the low tide minimum in distance from the bottom.
And Drew, what's going to happen if you touch those bottom weights down? You're going to be in big trouble?
Yeah, great question. Thank you, Greg. The only thing that happens is that it stops profiling until the wire becomes taut again. And so for a short period of time, you'll have just the same as if you attach the sensors to a fixed place on the wire in a regular mooring. There's no risk of damaging the system by doing that. And as soon as the tide comes in, you will be back to profiling. And if you don't believe me, you can look at my papers from my PhD thesis that have some gaps in the wire walker profiles that are in fact associated with sitting the weight on the ocean floor in a moored mode. So I learned the hard way, but I still got a PhD. And we didn't lose any instruments, and they kept working afterwards.
Great. Is who else have we got online who's ready for a question?
I see a question in the chat from Ming Feng. Ming, I was showing the spice. Spice, as you may know, is simply the on isopycnal variability of temperature and salinity, the covariability. And isopycnal is a single density class, but it can be made up of many different combinations of temperature and salinity. And so it's very useful because we can see things in the spice field, which is the compensated temperature and salinity variability that is on the isopycnal. So we can actually say, okay, this water is different than that water. Even though it's got the same density value, it's got a different spice value. And that means that dynamically, it might not change the internal wave field or the mesoscale or whatever, but it's very good for water tracking. And I've used it in that, I used it in that image specifically to show the difference between things that are blowing around, so we call it vection or currents, and changes that are associated with the biology. And it's the divergence between those two fields, the difference between the nitrate anomaly and the spice anomaly on an isopycnal that clearly implicates the biology in the process, rather than it's just, oh, it came from somewhere else.
Have we got anybody brave enough to ask a question live?
Any questions? You know, if you have questions about the vehicle, you know, the the different kinds of instruments we've used, the different scientific questions we've tackled, your own science, and how you might tackle it with the wire walker. I'm very happy to hear what you're doing, and I can make some suggestions based on my experience on how the wire walker helps in some situations.
Yeah, excellent. And what about biofouling, Drew? Do you find it the mechanics are affected by biofouling?
Yeah, great question. So the mechanical system is not. In fact, it's sort of self-cleaning because it's constantly grabbing and clutching and declutching on the wire. So the wire and the cam stays clean. The vehicles are pretty resistant to biofouling because of the rapid cycling in the vertical. You can still get biofouling, particularly for very shallow deployments in the tropical oceans and very long deployments. But bugs do not like going from the sunlit surface ocean to 500 meters depth and back every less than once an hour. There's very few organisms that can tolerate that type of environmental variability. There are some, and so you have to be cognizant. But we've been happily insulated from serious biofouling problems because of the rapidity of the vertical travel.
Yeah, excellent. Thank you.
I have one live question. So any commentary on typical mooring configurations that you use on the wire walker, let's say for 200 meters depth, but if you want to comment on any particular depths, just noting that the drifting setup that it was originally set for was a lot simpler than lots of different potential mooring configurations.
Yeah, great question. So we've used the whole gamut. So we've gone, my PhD work, and we continue to do this. We use very light ground tackle that we deploy off of a small rib or whaler. That's something like a 15 kg or smaller Danforth or Bruce anchor with a short shot of chain and a mooring line that's sort of similar to the water depth. That's great for short-term deployments off of small boats in water up to 100 meters or 150 meters of depth. After that, it becomes a little bit harder to hand deploy. So that's a great solution. Then we use what we call a reverse catenary mooring for bigger moorings, up to and including full ocean depth. We've just deployed 3-month-long full ocean depth 500-meter wire walker on top of a 4.5 kilometer taut mooring. That's a 36-inch sphere on many floats holding up the 4,500-meter tall mooring, an inductive swivel on the top of that, and then a catenary, a reverse catenary, where there's a line that goes up from the top of the taut mooring. There's floats and then weights, and then that connects to the bottom of the plunge weight. All inductively linked. So we have communication from the surface buoy through the wire walker profiling wire to the instruments on the wire walker, through the catenary to the surface, to the subsurface float, and to all the inductive instruments below down to 5,000 meters depth. So we use those reverse catenaries and smaller moorings, shallower moorings, as well. That works pretty well. However, the difference is the reverse catenary type mooring is always associated with very heavy bottom weights and acoustic releases, aka one shot at getting your mooring back and not getting your anchor weights back. If you are, well, maybe not always, but that's the way we've always done it. If you are going to be recovering your gear and redeploying it many times, or you want to get all of it back, including the bottom weights, a simpler approach is just heavy concrete blocks and a short shot of a floating line up to a reverse catenary, or this sort of very simple anchor procedure that I mentioned, if you can tolerate it, given your local conditions and the water depths. And that was a very long answer, and I apologize for that, but we've been working on this pretty extensively in the last year or so.
Yep, no, that's great. Thanks, Drew.
Yeah,
if there's any published information on any of those setups, I'm sure Stefan will pass them on.
Yeah, we are just the NASA program that funded these full ocean depth moorings has just ended, and you know, we just finishing some nice Proteus DS simulations of that full ocean depth setup with the 500-meter wire walker on top, and we hope to have a technical paper of that out. You know, probably early 21 would be my guess, but I'm or mid 21. But I'm happy to answer any more questions if you want to email me.
Excellent. I see there's a question there with David's followed up from my question from the bottom, but reversing it, saying how close to the surface can you get accurate measurements, Drew? Yeah,
we go all the way up. With our small floats, we get the inductive cell of the CTD within a meter of the surface. There is a bit of buoy contamination and waves breaking around the buoy and you know, et cetera, that's common to any buoy system. But we get very, very shallow. The bigger the surface buoy, so for example, those air sea flux buoys that I showed have a long sting in the middle of them that is about 4 meters, I think, below the water line is where the top of the wire walker profiling wire was. So it depends a little bit on the surface package, but you know, if you want to get shallow and you don't have a huge buoy payload, that's right in our wheelhouse. Excellent. Yeah, and of course with the inductive conductivity cell, it's not affected like a pump-based system with air getting into it. Once it gets back into the water, it carries on as normal. So that's great. So I think that's a nice place to wrap it up, Drew. Thank you very much for doing that. We are over time, and I really appreciate you eating into your evening. Hopefully you can get off to something nice to eat now. But I really appreciate your time, and thank you everybody for attending and participating. And hopefully we'll see you next week when we grill Greg. He's left, but thank you, Greg, as well for your time. And if you do have any questions, we'll follow this up with an email, and we'll include the DMO contact details as well for getting a hold of Drew. And look forward to next time. So thanks everybody, and stay safe. Thanks everyone, and please do reach out if you have any questions. I'm happy to answer any questions that you have. And Steph, thank you very much for hosting. Okay, thanks Drew. Thanks everyone. Bye.